Alright, so this is going to be the last day of solving differential equations, and we have 3 examples to get through. These are all AP type free response questions. It says, consider the differential equation dy dx equals e to the y times 3x squared minus 6x. Let y equal f of x be the particular solution to the differential equation that passes through 1, 0. So part A says, write an equation for the line that's tangent to the graph of f at the point 1, 0. So essentially writing the equation of a tangent line. And then use that tangent line to approximate f of 1.2. So if we're going to write the equation of a tangent line, we need 2 things. We need a point and a slope. So my point is 1, 0. They're giving that to me. And my slope would be the derivative evaluated at 1. So if I want to evaluate the derivative at 1, I'm going to plug in x equals 1 to all my x's up here in the derivative, and I'll plug in y equals 0 to all of my y values up here in the derivative. So that would be e to the 0 times 3 and then 1 squared minus 6 times 1. If I simplify that, e to the 0 is equal to 1. 3 times 1 squared is 3. 3 minus 6 is negative 3. So this is 1 times negative 3, which is negative 3. So to write the equation of the tangent line, that would be y minus 0 equals the slope of negative 3 times x minus 1. So that is the answer to the first part. For the second part, it says use the tangent line to approximate f of 1.2. So if I plug in 1.2 to this equation, I get y minus 0, which is just y, equals negative 3 times 1.2 minus 1. So this is the same thing as negative 3 times 0.2. And negative 3 times 0.2 is negative 0.6. So my tangent line approximation is approximately negative 0.6. Part B says to find the particular solution to the differential equation that passes through 1, 0. So essentially, I need to go through all those steps of separating the variables and then integrating both sides, etc., etc. And they're giving me this initial condition of 1, 0. So taking this equation, to separate the variables, I would divide e to the power of y over to the left-hand side and multiply dx over to the right-hand side. So if I go ahead and do that now, I get 1 over e to the y dy is equal to 3x squared minus 6x dx. And then I want to integrate both sides. So if I integrate both sides, I get... on the left-hand side, 1 over e to the y is not one of our basic derivative rules. And notice that I can actually rewrite this as the integral of e to the negative y dy. So we'll come back to that integral in just a minute. On the right-hand side, however, 3x squared, if I integrate that, would be 3x to the power of 3 over 3, which simplifies to x cubed. And then minus 6x to the power of 2 over 2, which simplifies to negative 3x squared. And then plus c. So here's what we got so far for the integral on the right-hand side. If you want to verify that that's actually the integral, go ahead and take its derivative. It should put you back to where we were at the very beginning. On the left-hand side, however, we would need a U-substitution. So on the left-hand side, it requires a U-substitution. And I'll let you guys set it up if you want to look at it over here. So u would be the inside function, which is negative y, and then we would take the derivative of that, and etc., etc. But when we do that, you're going to notice that the derivative of negative y is negative 1, and then we don't need that negative, so we move it up to the other side. So essentially, the integral of this just becomes negative e to the negative y, and then equals x cubed minus 3x squared plus c. Now, notice that, again, if you want to verify that this is the correct integral, go ahead and take its derivative. If you take its derivative, it requires a chain rule where the inside is negative y, and so you do end up getting e to the negative y if you take that derivative as well. So, at this point, let's go ahead and plug in our initial condition of 1, 0 so that we can solve for c. So everywhere I see a y, I'm going to plug in 0, and everywhere I see an x, I'm going to plug in 1. When I do that, on the left-hand side, I get negative e to the negative 0, which is negative e to the 0, and e to the 0 is 1, so this is negative 1. On the right-hand side, I have 1 minus 3, so 1 minus 3 is negative 2. Therefore, c is equal to negative 1 plus 2, which is equal to 1. So going from there, I have negative e to the negative y equals x cubed minus 3x squared plus 1. And now I want to solve for y. I want to get y all by itself. So here are the steps needed in order to do that. First things first, we're going to have to need to get rid of this e, but before we get rid of this e, we have to get rid of that negative. So I can get rid of that negative by dividing by negative 1 on both sides. That gives me e to the negative y is equal to, and then all these signs change. So negative x cubed plus 3x squared minus 1. And then to get rid of the e, we can take the natural log of both sides. So if I take the natural log of the left and the natural log of the right, that gives me the e and the ln on this side are inverse operations, so those undo each other. So we have negative y left on the left, and then we have ln of negative x cubed plus 3x squared minus 1 on the right. And then last but not least, to get y by itself, we just divide by that negative. So y is equal to negative natural log of negative x cubed plus 3x squared minus 1. And that is my final answer for a particular solution to the differential equation that goes through the point 1, 0. All right, let's look at another one. This one is a little bit different. It has the same types of ideas in it, but it's just solved a little bit differently, so I'll go through it with you guys as well. It says the rate at which a baby bird gains weight is proportional to the difference between its adult weight and its current weight. At time t equals 0, when the bird is first weighed, its weight is 20 grams. It says if b of t is the weight of the bird in grams at time t days after it is weighed, then this equation holds true. So essentially the rate at which the weight of the bird is growing follows this equation. It says let y equal b of t be the solution to the differential equation above with an initial condition that b of 0 is equal to 20. So essentially similar in the sense that we're working with differential equations, but different in the sense that we're no longer working with x's and y's, we're looking at different variables. It says, is the bird gaining weight faster when it weighs 40 grams or when it weighs 70 grams? And explain your reasoning. So essentially we would just plug in those numbers here, and then we would evaluate to see if the rate that the weight, sorry, it's like a run on words here, the rate that the weight of the bird is changing is more, so is dB dt more at 40 grams or is it more at 70 grams? So if I plug in 40 first, I would get that dB dt is equal to 1/5 times 100 minus 40. So that's 1/5 times 60, so that's 60/5, which is equal to 12. And the units are, does it say units in the problem? Let's see, B is in grams, so grams per time. Where does it say time? Days, there we go. So B is in grams, and then time is in days. So it's going to be 12 grams per day. That's how much weight it's gaining every day. And then if I plug in 70, dB dt would be equal to 1/5 times 100 minus 70. And 100 minus 70 is equal to 30, and 1/5 of 30 is equal to 6. So that's 6 grams per day. So in conclusion, the question says, is the bird gaining weight faster when it weighs 40 grams or when it weighs 70 grams, and explain why. We would say the bird is gaining weight faster when it weighs 40 grams because, and then essentially just summarizing what we said here, because when we evaluated at both of the weights, we found that the rate of change was faster for, or larger for 40 grams. So because the rate of change is larger for 40 grams. And we don't need to go into too much more detail with this explanation because our work is also enough explanation. So when it says explain your reasoning, essentially they just want to see that you actually evaluated both of them to show that it's gaining weight faster at 40 grams. They don't want you to just make a 50-50 guess and get the points from it. So that's why they say to explain your reasoning, but the work is mainly the reasoning in this case, as long as we explain that it's growing faster at 40 because it's a higher number. Part B says to find the second derivative d squared b dt squared in terms of b, and then use that second derivative to explain why the graph of b is not able to resemble this graph over here. So, to find the second derivative, first of all, notice that we have this constant multiple out front, which we could leave out there, but I'm actually going to distribute it into both of these terms just so you guys can see it a little bit easier. If I do that, I get that db dt is equal to, if I distribute that 1/5, I have a 1/5 of 100. So 1/5 of 100 is equal to 20 minus 1/5 of b. And the reason I want to do that is because now when I get to take the second derivative, d squared b dt squared, 20 is a constant. So the derivative of a constant is going to be 0, and so I like to see it written that way. Then this negative 1/5 is a constant multiple. It tags along for the ride. And the derivative of b, remember that b is not the important variable in this problem. T is the important variable. So when I take the derivative of b, I have to take it using the chain rule. So the derivative of b itself is 1, but the derivative of the inside, since b is a function of t, would be db dt. So this is negative 1/5 times 1 times db dt. All right, but they want it in terms of b. So notice that right now our second derivative is actually in terms of the derivative itself. So the second derivative is in terms of the first derivative, but they want the second derivative in terms of b. So all we're going to do here is we're going to take the first derivative that was given to us in the problem, and we're going to substitute it in here to this equation so that we can rewrite our second derivative, but in terms of b. So this will be negative 1/5 times 1/5 times 100 minus b. If I do a little bit of simplification, that would be negative 1 over 25 times 100 minus b. And I can leave it like that. The second derivative can be written that way. So this is an answer to that second part, to part B. That's the second derivative. It says use that to explain why this graph over here could not be the graph of b. And for the explanation in terms of why this couldn't be the graph, I'm not going to write it out word for word, but I will talk about it a little bit. I think it mainly has to do with the fact, and the explanation I would give mainly has to do with the fact that when we're looking at the second derivative, we're essentially looking at the concavity. And so analyzing this second derivative, it shows us that by looking at it, we have a 0 at 100. So essentially if I plugged in 100 for b, we would get 100 minus 100, which would be 0, and that would be a point of inflection as long as it changed direction, which it would. But thinking about 100, that would be when the bird weighs 100 grams, that's where it changes concavity. But if you look at the graph here, we can see that it's concave up, and then right about here, it changes to be concave down. But if you look at the weight, so I'm looking at the y-axis, I'm not looking at the x-axis. If I look at the weight around this point where we have this point of inflection, it's nowhere near 100. It's in between 20 and 100. So it's much closer to like 60 or something like that than it is to 100. And so since that point of inflection is not at 100, but instead rather in the middle of 20 and 100, I would say that's probably the main reason why I would say this could not be the graph. So it should be concave down actually. If you plug in any number less than 100, so for example, if we plugged in 60, we would get 100 minus 60, which is 40, and then negative 1 over 25 times 40, which is a negative number. So all these numbers down here, until we reach 100, are all going to be concave down. So the shape of this bird's weight growth kind of looks like this. It looks kind of like a logarithmic curve until we get to 100, and then it starts looking exponential again. So anyway, that would be my reasoning for why I don't think this graph resembles what B could actually look like. Last but not least, part C says using separation of variables to find y equals b of t, the particular solution to the differential equation with an initial condition of b of 0 equaling 20. So we're going to come back up here to this equation, our first derivative. We're going to separate the variables. Now, notice that I don't have a t anywhere in here, so when I move dt over to the right-hand side, I don't have any t's to integrate necessarily. And I don't need to necessarily move this entire thing over to the left-hand side. I just need to move the part that has a b in it. So this 100 minus b is the only thing that I actually want to move to the left. So let me rewrite this. db dt is equal to 1/5 times 100 minus b. So all I'm going to do is I'm going to move the 100 minus b over to the left-hand side. And I'm going to multiply by dt on both sides. So what that's going to do is it's going to help me separate my variables by getting dt over on the right-hand side and the b's on the left-hand side. So this is 1 over 100 minus b db is equal to 1/5 dt. So if we integrate both sides, on the left-hand side, I can actually do a U-substitution. If I set u equal to 100 minus b, then du is equal to -1 db. And I don't need that -1, so I can move it over. That's negative du is equal to db. If I do a little substitution, 100 minus b gets replaced with u, and db gets replaced with negative du. So this is negative integral of 1 over u, make that the thinner one, negative integral of 1 over u du is equal to the integral of this side. Because there's no t's over here, this is just a constant multiple, so it tags along for the ride, and then the integral of the lack of a t, I guess you could say, is that a t appears. So that's 1/5 t plus c. And then over here on the left-hand side, the integral of -1 over u is negative ln of the absolute value of u. And if I replace u with what it equals, that would be putting u back in, which is 100 minus b. So I'm going to plug that in right here. I'm going to erase this just so I have a little bit more room. So that's negative ln of absolute value of 100 minus b is equal to 1/5 t plus c. Now at this point I can actually plug in my initial condition. So everywhere I see a t, I'm going to plug in 0. Everywhere I see a b, I'm going to plug in 20. And I'm getting that from right here, my initial condition. So this is negative ln of 100 minus 20 is equal to 1/5 times 0 plus c. So on the right hand side I just have c. On the left hand side I have 100 minus 20, which is 80. So this is negative ln of 80. Plug that back in here, which gives me, and if it's okay with you guys, I'm gonna really quickly free up some space here so we can continue our work here. Alright, so let me continue up here. So that gives me negative ln of the absolute value of 100 minus b is equal to 1/5 t and then minus ln of 80. So we need to solve for b now to get b all by itself. We got to get rid of this ln, but before we can get rid of this ln, we have to get rid of the negative. So let's divide both sides by a -1. That gives me ln of the absolute value of 100 minus b is equal to negative 1/5 t plus ln of 80. Then to get rid of the natural log, remember that's where we raise both sides with the e power. So e to that side and e to that side with all that. On the left-hand side, the purpose of doing that is because e and then to the power of ln, those are inverse operations, so those undo each other. We're just left with the absolute value of 100 minus b is equal to, on this side we have e to the negative 1/5 t plus ln of 80. Now, I will remind you, remember we talked about properties of exponents in a previous video. We said that if we're adding two exponents up here, we can separate them by multiplication. So this can essentially be separated as e to the negative 1/5 t times e to the ln of 80. Oops. E to the ln of 80. And then e and ln are inverse operations, so those go away. So this is just 80. And I can write it in front. So I'm going to write this as 80 e to the negative 1/5 t. is equal to absolute value of 100 minus b. Now, we have to take care of this absolute value because we don't want this absolute value bars here when we're solving our problem. So remember, in order to decide whether or not we need to utilize the absolute value or activate the absolute value, let's look at our initial condition one more time. If I plug in 0 here for t, I get 0 times negative 1/5, which is 0, e to the 0, which is 1, and that equals 80. Now, I want it to be what am I trying to say? I want it to be a positive 80 because I want 100 minus 20 to be positive 80 as well, which means I did not need to activate my absolute value. I did not need to use it because 100 minus 20, which is my b value from my initial condition, 100 minus 20 is a positive 80, so I don't need to activate that in order to get a positive 80. So I do not need my absolute value bars. I can just rewrite them again without absolute value. So this is 100 minus b. If I did, by the way, just a side note, if I did need to use these in order to get the number I wanted on the other side, that just means you have to make the other side negative. So you would have still dropped the absolute value bars, but on this right-hand side, you would just made this negative. But we did not need to utilize it, so I do not need to make that side negative. E to the negative 1/5 t. Subtract 100, so we get negative b equals 80. E to the negative 1/5 t minus 100. And last but not least, we can divide by a negative 1. So that gives me that b is equal to negative 80 e to the negative 1/5 t plus 100. Final answer. Whew, that's a lot of work. All right, so there's my answer for part C, the particular solution to the differential equation. All right, and the last one for today is here. It's similar to the one we just did, so I'm going to encourage you guys to pause the video right here and try as much of it as you possibly can. If you get stuck on a specific part of it, then do me a favor and skip it. So do as many of these parts as you can to the extent that you can. And then when you watch the video, you can kind of fill in the blanks and figure out where you went wrong so that you guys can kind of gain insight from that. But like I said, I'm going to pause the video and I'm just going to write out the whole solution. I'll go back at the very end and explain it, but you're not going to see me talking through it word for word as I do it. I'm just going to pause the video and do the whole thing and then show you what the answer is. So do me a favor, pause your video now, and then catch up with me after you've done as much as you possibly can. Alright, so I didn't get a chance to finish it yet, but I kind of ran out of room and I wanted to start erasing some stuff. So before I erased anything, I wanted to show you guys what I got so far, and then we'll talk through the rest of it together. So for the first part, well, it says, at the beginning of 2010, a landfill contained 1,400 tons of solid waste. That's an initial condition, what they're telling you originally. It says the increasing function W models the total amount of solid waste that is stored in the landfill. The planners estimate that W will satisfy the differential equation dW dt equals 1 over 25 times W minus 300 for the next 20 years. W is measured in tons and T is measured in years from the start of 2010. So part A says to use the tangent line to the graph of W at T equals 0 to approximate the amount of solid waste that the landfill contains at the end of the first 3 months, which they're giving you a little hint that 3 months is only a portion of a year, so time equals 1/4 of a year. So in order to write the equation of a tangent line, we need a point. So our initial condition is our point, T equals 0, and they gave us the initial condition that it started out with 1,400 tons of solid waste. Then our slope, I plugged in 1,400 to our differential equation. So for W, the tons of solid waste, I plugged in 1,400. And then I got 1,400 minus 300 times 1 over 25, which ends up being 1,100 times 1 over 25, and that's 44. So using our point and our slope, I wrote the equation of the tangent line right here, y minus y1 equals m times x minus x1. And then I plugged in 1/4 for t in order to evaluate what the estimate is of the amount of waste after 3 months. So 1/4 of 44 is 11, and then if I added 1,400 over to this side, 11 plus 1,400 is 1,411 tons, and that's my approximation. By the way, I noticed that I shouldn't really use y's and x's here. I should use w and t, but that's fine. I get the point. And I think the reader on the AP test as well would be forgiving as long as you did it correctly. Ideally, I should have used a w, though, and a t here, but anyway. For part B, it says find the second derivative in terms of w, so that's what I did first. Notice that just like we did in the last problem, I wanted to distribute the 1 over 25 to both of these. So 1 over 25 times w, and then 1 over 25 times 300 is what I got there. When I take the derivative of this constant is 0, and the derivative of 1 over 25 times w is 1 over 25 times 1. Remember, the derivative of w is 1. Times the derivative of the inside, so dw dt. Because they want it in terms of w, I just replaced this expression, dw dt, with what it equals. I replaced it with 1 over 25 times w minus 300. From there, I just combine a little bit of like terms. 1 over 25 times 1 over 25 is equal to 1 over 625, and then that w minus 300 I left alone. So this is part of my answer for part B. This is the expression for d squared w dt squared in terms of w. Then they asked us to determine whether or not part A is an underestimate or an overestimate at 1/4, at t equals 1/4. So the way to figure it out is from the concavity. If it's concave up, then the tangent line would lie below the curve. If this indicated that it was concave down at 0, then the tangent line would lie above the curve. Let me show you a little picture of what I mean. Here's concave down, and here's what a tangent line looks like on a function that's concave down. So any function that's concave down, the tangent line will be above the curve, and the approximation would be an overestimate. But any function that's concave up, the tangent line will lie below the curve, therefore it would be an underestimate. So because when I plug in the initial condition here, so I'm not plugging in t equals 0, I'm actually plugging in the amount of waste, because w is my variable. So if I plug in the initial condition of 1,400 tons, I get 1,400 minus 300, which is 1,100. And then 1,100 times 1 over 625 is a positive number. That's all I care about. So what I said is the estimate is an underestimate because the second derivative is positive when t is equal to 0. So I should have shown it. I just talked through it with you guys. It would have been better if I actually showed that it was positive when t is equal to 0. I said, therefore, w is concave up at that point, and the tangent line is below the curve. So I even drew a little picture to show that concave up has a tangent line below the curve, therefore this is an underestimate. For part C, they want us to find the particular solution, so I moved w minus 300 to the left, and I moved dt to the right by multiplying it. The integral of 1 over w minus 300 is ln of that absolute value. The integral of 1 over 25 is 1 over 25t plus c. I used the initial condition of 0, 1,400 to solve for my c value, which I got to be ln of 1,100. And I plugged that back into the original equation, and that's where I stopped. So far I have this original equation with my c value all plugged in. So now I'm going to take a minute and erase some of the stuff I've already done, so I have a little bit of extra room to show you guys the rest of this problem. Alright, there we go. So I'm going to take this now, and way up here, I'm going to continue our work. Alright, so to get rid of this natural log, I'm going to take e and raise both sides to the power of e. So this is e to the ln of the absolute value of w minus 300 is equal to e to the 1 over 25t plus ln of 1100. On this side, e and ln are inverse operations, so we're just left with the absolute value of w minus 300 is equal to, on the right-hand side, remember that the properties of exponents say that if I'm adding these two things, I can separate them as e to the 1 over 25t times e to the ln of 1100, and the e and the ln are inverse operations, so those undo each other, so I'm just left with a constant multiple of 1100. So I'm going to write this as 1100 e to the 1 over 25t. And again, if you're not quite sure where we got that, go back and look at the last example we just did. We did one exactly like it, just with different numbers. Let's see if we need this absolute value. So if I plug in 0 for t, I get e to the 0, which is 1 times 1100. And then on this side, my initial condition was 1400. If I plug in 1400 on this side, I get the absolute value of 1100. So no, I do not need to activate the absolute value, which means I can just drop it. 1100 e to the 1 over 25t. And last but not least, I just need to isolate by adding 30 to both sides. So 1100 e to the 1 over 25t plus 30. And that is my particular solution to this problem. Final answer, and that is the end of solving differential equations.